Welcome to possibly the last part of Chapter 14. We'll see how that dream goes. I think I'll leave it zoomed out in order for you to better see this first demonstration. When I'm standing on this side, I can't tell what you see, what I look like, but I think we're okay. I want to illustrate for you, before we move on, going back to an old concept here, the idea of buoyancy in air. Remember, the upward buoyant force on an object in air or in water, the upward buoyant force will be equal to the weight of the displaced fluid, displaced air or displaced water. So here I have a helium balloon. This helium balloon wants to go upward because it's displacing an amount of air that has more weight than its own weight. How can that be? Because helium weighs less than air. Does helium have weight? Yes, helium has weight. But it has less weight than the surrounding air. So the displaced air weighs more than the balloon itself. Thus, there's an upward net force called the buoyant force, which makes the balloon want to rise. Now, by attaching this cup to the bottom of it, maybe I can put something else in the cup just to really emphasize this. What can I put in there? Oh, let me simply attach this little clip that came with the balloon. Now, the mylar plus the helium plus the ribbon plus the cup, or what's left of the cup, plus the clip all weighs more than the displaced air. Since the balloon and package itself weighs more than the air it displaces, then the net force will be downward. And there it goes. Of course, notice please that it falls more slowly than the usual 9.8 meters per second, because the net force is not its full weight. The net force is its full weight minus the weight of the displaced air. Fascinating. Now, it occurred to me once, just kind of stumbled on this by accident during my college days, playing with a helium balloon. Is it possible, if I remove the cup entirely, then the balloon will of course go up. If I attach the cup, then the balloon will go down. Doesn't it make sense that there should be something right in between someplace? Yes, there is. If I can trim away enough of the cup, and I'm running out of things to trim here. This, by the way, is an insulated cup. It weighs too much. An ordinary paper cup works much better with this. With the insulated cup, I've got to cut away quite a bit to make this work. I'm going to cut away a little more, tear away a little more. And see, I like to use a cup so that if I tear away too much, I can put some back in. Of course, there's not much in to put it back into, but that's getting closer, but I still need to take off some more. Let's just take off about that much and see how that does. That's pretty good. It's still tending to go down. Wonder if I can just take off a piece of the ribbon, if that is enough to make a difference. Well, it will make a difference, but how much of a difference? That's pretty good, but not good enough to make me happy. Gonna take off some more cup. That's pretty good. It still wants to go down a little bit. Let's take off a little bit more. Where can I find a place to take some off? Okay, a little bit more off there. And let's see if that was too much. That's pretty close to equilibrium. It's still tending to go down. I don't know if it's because of air currents. Right now the air conditioning system is off, so it shouldn't be air currents. Let me take off a little bit more, and maybe a little bit more, and see if that is perfect. That's pretty good. Right now the balloon is behaving as if it were weightless. If I tap it this way, it goes that way. Of course, air friction causes it to stop. I can tap it down, it goes down. I can tap it up, it goes up. Tap it, stop it, tap it again, make it go down, tap it, stop it, push it that way, tap it, stop it. F equals ma seems to be working perfectly. It's behaving as if it were weightless. You can play with this all day, just as if you were on the space station. It's pretty cool. So what's exactly happening right now? I have adjusted the weight of the cup, the ribbon, the mylar, and the helium. The weight of the total package is now equal to the weight of the air it all displaces. Therefore, the upward buoyant force is equal to the balloon's downward weight. Everything cancels, and it goes nowhere. Or if I make it go someplace, it continues going that direction until acted on by another force. Of course, air friction is the force that stopped it just now. It continues till I stop it, or bounce it the other way. And this is kind of cool. You can send messages to your friends. It's a nice way to send a message, a note to a student in class, and the teacher will never notice. Just put it on a helium balloon with the proper adjustment here, put your note in there, trim off some more cup to make it equalize, to make it balance out, and then say, "Hey, Jack, while Mr. Pierce's back is turned, quick." And you launch the balloon toward Jack, and it will eventually drift over. Well, it'll follow the air currents in the room, but you have a good chance of getting it eventually over to Jack that way, and Mr. Pierce will never know. Or, well, if he turns around, he'll know. Anyway, so, buoyancy. We now switch over to another concept. Oh, no, there's another old thing. I finally brought down my Cartesian diver, we call this. Inside this bottle there is a glass tube, a test tube, with some red tape wrapped around it, and an air bubble in there. Right now, it's floating. I like to play tricks on little kids with this. It's so much fun to make it go down and not tell them why it's going down, and just kind of mess with their minds. I like to do the force thing. Down, 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 or then I go up, stay, stay. Oh, right there, stay. And it goes up. And it's fun. It's Cartesian dive. What's going on? When I squeeze the bottle, the water in the bottle is nearly incompressible. As far as I'm concerned, it is incompressible. When I squeeze the bottle, that pressure that I'm adding to it goes into the test tube and forces the gas bubble, the air bubble in the test tube to get smaller. In fact, I hope you can see this. There's no way I can test it right now. But if I get up here close to the camera, it should focus on me pretty well here. Okay, now watch. Can you see the bubble? I have no idea if you can see it or not. But if you can see that bubble, watch what happens when I squeeze the tube. Watch the bubble. As I squeeze, the bubble gets a whole lot smaller. When I unsqueeze, the bubble gets bigger and the test tube rises. When I squeeze it, it's displacing less water because now water has gone up into the test tube. It's displacing less water now. So it sinks. When I release, the bubble gets bigger. It's displacing more water. There's more buoyant force. The test tube goes up. So whether or not you can see the bubble, I hope you can because it's kind of cool. But if you can't, just trust me. You can actually see the bubble change size. I should have done this with a different color liquid. No, that wouldn't work. Anyway, moving on. Now, back to the Bernoulli principle that we introduced last time. Bernoulli principle, that the pressure, the internal pressure, the pressure inside a fluid that's moving is lower than the pressure inside a fluid that's sitting still. I tried to illustrate that last time with that diagram of a tube that starts big and gets small. And believe it or not, air bubbles will actually expand when they get into this small part. You think, well, it should be just the opposite. Yes, I know, it hurts my brain too. It seems like it should be the opposite. But allow me now to try to explain why the pressure actually decreases, why the bubbles will actually get larger when they enter the confined area. Consider this. A typical traffic jam. I have no idea where this picture came from, found it online. We've got, apparently, it looks like an ambulance. There must be an accident up ahead here. But we've got all this traffic backed up way back here. These cars are jammed up against each other. There might be some accidents going on in here, impatient drivers banging into each other, who knows. All the honking and everyone's they're under high pressure. They are all upset and can't go anywhere. A lot of pressure back here. But what happens when they finally get down to a single lane? Have you ever experienced this? Once you get down to a single lane, what happens? It opens up. And now you can move faster. Now there's less pressure. You can zoom on ahead. Now there's more distance between the cars. Once you get into that narrow area, you can now move fast. That's how it is with fluids. And here's my little diagram to further illustrate. Oops, too far. Back up. There we go. We got all these cars coming in here, and they're all being channeled down to a single lane. All these guys are getting impatient with each other. We got, oh, there's an accident going on right there. There's another accident there. Oh, there's another accident. This guy's getting kind of impatient trying to butt into that line because he thinks that one's going faster. And it's just, oh, there's an accident there. These guys all run. There's high pressure going on here. But as soon as they get to the narrow part of the opening, they start flying through here, and they got plenty of space now. There is less pressure. They're moving faster. There's less pressure. And also keep in mind this. The cars that go in at this end have to come out at that end. So as cars slowly enter here, suppose 1, 2, 3, 4, 5, suppose these last 6 cars enter in a minute. Well, we need to have 6 cars coming out here in a minute, which means they're going to be moving a lot faster, but the pressure is lower. That's the best I can do to try to explain the Bernoulli principle, but I can demonstrate it with something called a Bernoulli bag. Yes, there is a thing called a Bernoulli bag. I've already pre-inflated this. I'm going to inflate it a little farther. This took me about, that's about 6 or 7 breaths worth. I'm going to put a little more in. That's about 8 breaths worth. Taking the biggest breaths I can and emptying my lungs into the bag, including all the coronavirus and everything else, all now in this bag. Interesting thought. So now what I'm going to do is empty the bag out of my 7 or 8 breaths. I am now going to fill the bag just as much with just 1 breath. I don't know how well you're going to be able to see this. I'm going to kind of prop it up here. I have no idea how much of that you can see. But now, 1 breath. Excuse me. Here we go. Oh, that was pitiful. That was pitiful. Surely I can do better than that. Back in my younger days, I could practically fill this whole bag with 1 breath. Oh, that was much better. Look at that. Look at that. That's almost as much as was in it before, and that's 1 breath. Are my lungs that big? No, my lungs are not that big. How is that possible? Let's see if I can fill it up like twice as far with 1 more breath. That wasn't twice as far, but that's a good bit farther. What's going on? When I breathe into or blow into the bag, with my mouth not on the bag, but my mouth away from the bag, my breath is moving fast. That means the pressure in that moving breath is lower. So the surrounding normal air pressure is going to rush into the area of lower pressure. So my low pressure breath is being joined by the high pressure air around it, being added to my breath, and thus dramatically increasing the amount of air going into the bag. Bernoulli principle. Another, let's see, one more thing about Bernoulli principle. For this one, I'm going to have to change the camera angle here and point you at my little demonstration table. Okay. Now, consider this. Here I have a house. Okay. A very strange little house. But I'm going to put some moving air going through the inside of the house. The Bernoulli principle says if I blow under the house, there should be lower pressure in here, but normal pressure on the outside. If I've got low pressure inside and normal pressure outside, what should happen? Yeah, it's going to cave in. Let's try. and it goes flat instantly. One might have thought that the air going in here would cause it to blow upward, but it does not. Every time it goes down. Because the moving air going under here is lower pressure than the normal air on the outside that's not moving, and it gets crushed by the air. Same thing happens in hurricanes. Oops, let me realign. Okay. There we go. In hurricanes, you've got a house, and you've got a really strong wind blowing across the roof of this house. You're going to have low pressure on the outside where this moving air is. Low pressure outside, normal pressure inside. It can lift roofs right off the house. It happens. I've seen videos of large corrugated metal roofs on like a warehouse being lifted right off by hurricane winds. Low pressure where the air is moving, normal pressure where it's not moving. The higher pressure here pushes the roof right off. The wind is not lifting the roof. No. What's happening is the high pressure inside is pushing the roof up. Let's see, what other demonstrations? Here's one more demonstration of the Bernoulli principle. This is one of my favorites. This is pretty cool. I've never tried to do this in front of a camera, so I don't know quite how well it's going to work. And this gets kind of noisy, so you might not be able to hear me. But you don't have to hear me, just watch. First I want to take a quick peek at my camera and see exactly what is in view. Okay, I can see from over there to over there, top, bottom. Okay, I just have to try to keep this demonstration in the view of the camera. I have an air supply here. It's called an air supply. It's a reverse vacuum cleaner. It blows instead of sucks. Okay, so I'm simply blowing things. Now if I do this, you can see the balloon wiggle as it's sort of, okay, there we go. Yeah, that kind of proves it's blowing, right? All right, I'm going to turn the volume of the air down some. And now, as I crouch down so I can control the speed, behold. All right, I now have the balloon being supported. Oops, okay, a little too, need some more air here. All right, the balloon is now being supported by the flowing air. Pretty cool, but not horrifyingly surprising. One might wonder why the balloon doesn't fall to one side or the other. We'll get to that in a minute. But here's where it gets really cool. Watch this. I can turn, if I do it carefully and slowly, I can turn my airstream sideways and the balloon continues to be supported. Now watch this. See if I can get away with this without dropping it. I'm going to lower my airspeed and bring the balloon in closer to myself. Then I'm going to increase the airspeed and push it away. And then one question might be, how far can I tilt it before it finally does fall? Let's see if we can find out. How far can I tilt it? How far? How far? Well, that's pretty good. Can I bring it back in myself now? If I do too quickly, I would definitely lose it. Doing it slowly. Now pick up the speed. How fast can I go? Pretty neat. Look at that. From this angle, it looks like I'm at about 45 degrees and it's still hanging in there. How far can I go before I lose it? And I'm somewhere around 60 degrees now, maybe not. Oh, there I lost it. All right, so what's going on there? How in the world does that work? Okay, let's take a look. I've got the balloon here. I've got this air flowing. Let's do the vertical first. I've got the air flowing out of this thing. Air is going like this. All right, remember now, again, Bernoulli principle, where the air is moving, you have lower pressure. So on both of these sides, we have low pressure. What happens if the balloon tries to fall out to one side or the other? If the balloon tries to fall out on this side, now we have all this moving air over here, where there's low pressure. There's no moving air over here, so we've got high pressure. So what happens? The normal atmospheric pressure here, the high pressure, pushes the balloon right back into the stream, into the area of lower pressure. Then what happens if it tries to go too far the other way? Same story. Here we've got high pressure pushing the balloon back in this way toward the area of low pressure, so the whole thing stays stable. It works just exactly the same way when the hose is tilted sideways. Here's your balloon. You've got your blowing air, kind of like this. And this time, you've got low pressure on this side. You've got higher pressure on this side as the balloon tries to fall. Why would it try to fall? Gravity. As the balloon tries to fall, now you have lower pressure here where the air is moving, higher pressure here where it's not moving. It pushes the balloon up until it reaches a point of equilibrium, just holds it there. Pretty cool concept. Bernoulli principle. It's true. It works. Pretty bizarre. Okay, now, was there another demonstration I needed to do for you? Yes, one more thing. This has nothing to do with the Bernoulli principle. I'd forgotten about this earlier. A little clever device. I was inspired to try this by a demonstration I saw at the Science Expo in DC years ago, and I decided to make my own device here. I have a little rubber tube going from the side arm of this flask down to the bottom of the tube here. I'm now going to put my mouth over the flask and inflate the balloon. Watch what happens. The balloon is inflated, but it's staying inflated. Did I tie off the end of the balloon? No, I didn't. Can you see down there? Can you see? You're looking right into the mouth of an inflated balloon. Pretty cool, huh? So, it's some kind of optical illusion. Well, watch this. I'm going to take a pencil. I can put a pencil right down inside that balloon and take it back out again. No problem. The pencil is inside the balloon. So what in the world's going on there? Well, when I inflated the balloon, I pushed the air out of the flask. Air in the balloon, the flask has little air in it now. I put my finger over the mouth of the sidearm here. Over the, well, I should say over the what do you call that? The port of the sidearm, I guess. Get my finger over the hole. There we go, it's a hole. That means that the air, no air can get into the flask. So inside the flask itself, I have low pressure. Inside the balloon, I have high pressure. Well, the high pressure wins. The balloon stays inflated. If I take my finger off of this little opening, that will allow air to go back into the flask, equalizing the pressure and allowing the balloon to deflate. Yes, in case you're wondering, I can not only inflate the balloon by blowing on the top, but I can also inflate the balloon by sucking on the sidearm, which is considerably more difficult. I'm going to get dizzy doing this. There. Okay. I did that by sucking on the sidearm, thus decreasing the pressure in the flask. Normal atmospheric pressure simply goes in and inflates the balloon because the pressure down here is greater than the pressure surrounding the balloon inside the flask. There's another little trick that I've done that I'm not going to do now because it makes a mess. Do I have any water here? No, I don't have any water handy, so I can't really do it for you, which is a good thing because it would make a mess. But if I inflate the balloon, then pour water into it and put it in a pan and release, we get a water volcano. The water goes gushing up out of there. It rises about maybe that high as it gushes out, makes a mess all over the floor. It's kind of neat. Get yourself a sidearm flask and try it at home. If you want to order one on Amazon, it's called a sidearm flask. Okay, were there any other cool demos I needed to do for you before we try to finish out this chapter? I think that's it. I feel like I'm forgetting something, but no, I've done it all. There's nothing more I can do. So that is the Bernoulli principle. Another way, Bernoulli principle also applies to plane wings. Suppose that's an airplane wing. The airplane wing is more rounded on the top than on the bottom. There are other reasons why a plane is able to fly, but this is part of it. As the air hits the wing and goes around here, and around here, and around here, notice the air up here has to go a larger distance to get over to this point. This air is going a shorter distance. Therefore, this air is actually moving a little faster across the surface. Well, if this air is moving faster, there's lower pressure up there. There's higher pressure down here. Who wins? Well, the high pressure wins over the low pressure, so there's an upward force, the Bernoulli principle. And is there anything else? That pretty much. There's some other things that Mr. Hewitt points out over on page 280, 281, things that are not critical. Oh, the atomizer idea, figure 14.24 is pretty cool. You can actually do this, and did I bring the right materials to do this for you? I don't think I brought the right stuff to do it. No, I didn't. So I've got all my materials are upstairs in the science lab, and I've got so much stuff down here already. There are so many things I forget to bring down. So I will not show you my little homemade atomizer. That's it for the Bernoulli principle. He has a short discussion of plasma. Plasma is the fourth state of matter. You've got solid, liquid, gas, and then you have plasma. Plasma is what happens when your gas gets heated to the point where electrons come off of the atoms. So you end up with charged particles, positive particles and electrons flying around out here. So those particles are charged, but the number of positives and negatives is still equal, so even though they're separated from each other, the whole package, the whole gas is still neutral. You don't find plasmas just floating around in the air, but you do find plasmas in, for instance, fluorescent lights. You find, where else can you find plasmas? Oh, a candle flame itself is a form of plasma. Plasmas are very good at conducting electricity because they have a whole bunch of free electrons flowing around, and those free electrons can move through the plasma, so plasmas conduct electricity. Anything else that's important to know about plasmas? That's probably all you really need to know. It's not a major topic in this chapter and will not be a major topic on the test. All right. Now, I'm a little torn here because I have my Chieftain Institute students and I have my Covenant Life students. The Covenant Life students are accustomed to having assignments in two parts. The Chieftain students are accustomed to having those same assignments in one part. So how shall I do this? I need to give you a review assignment to help you to think these things through. Tell you what, I'm going to go ahead and split it into two parts. So here's part one. I'm going to describe both parts. Covenant Life. We have come up with a new schedule, as you're aware, I hope you're aware, where physics, unlike the other sciences, physics only meets on Tuesdays and Thursdays. I will only give assignments on Tuesdays and Thursdays. I will only expect you to submit assignments on Tuesdays or Thursdays, except for tests. Tests, I believe, our physics test assigned day of the week is Fridays. No test this Friday. But Covenant Life, part one will be due on Wednesday. No, can't do Wednesday with you guys. Part one will be due on Thursday, and part two will be due the following Tuesday, a week from today. Chieftain, I'll expect you to do both parts, and I would expect those parts to be done. Oh, I'm so discombobulated. This Thursday is the day I would normally give the assignment, right? So that would imply that it will be due for you guys the following Thursday, unless I've messed up and I'm out of sequence. No, that's correct. This would be the week that I would give you the assignment, or is it the week I would give you the test? Hold on a moment, let me check my calendar. Tell you what, Chieftain people, I'll send you an email later to clarify what's going on. But for now, your assignment. Part 1 will be page 286, page 286. Numbers what? Numbers 1, 2, 5, 7, 10, 12, 13, 15 through 17. And question, where do I want to cut it in half? Okay, let's go a little farther. Then 20 and 21. That's part 1. Part 2 will pick up on page 287. If that's reasonable. Part 2, let's change colors. Part 2 will be on page 287, numbers 23, 24, no, let's do 23 through 26, then jumping down to 28 through 30, 28 through 30, then 32, 36 through 38, 36 through 38, and I'm going to have to lose a little bit of part 1 there, but that's okay, you know where it is. And after 38, 41, 44, and 45, 41, 44, and 45, and we'll stop it right there. Yeah, good enough. We'll stop there. All right, so Covenant Life people, assuming that I give you this on a Tuesday, this will be due the following Thursday. If I give this to you on a Thursday, it'll be due the following Tuesday. And then part 2 will be due the next Tuesday or Thursday. Chieftain, I'm not sure yet. Both parts due sometime. I'll email you that information later. All right, that's it. Hope this didn't go too long. I have no idea how long it was. See you later.